Look at a sealed flask of pressurized gas resting on a table. To our human eyes, the container rests in silence. But that stillness masks a different reality. If you zoom in to the microscopic level, you find a state of constant chaotic violence. Millions of particles are incessantly zipping around, slamming into each other and the glass walls in perfectly elastic collisions. Temperature represents a precise mathematical gauge of this internal kinetic energy. It is the microscopic motion of a gas translated into a macroscopic value. But it measures a very specific type of energy. A thermometer tracks translational speed, how fast a particle is moving from point A to point B along the x, y, and z axes in three-dimensional space. In a simple gas made of single atoms, like argon or neon, injecting heat causes the atoms to translate faster. The temperature spikes immediately because there is nowhere else for the energy to go. That direct relationship holds for single isolated dots. But the physics change when the gas possesses a physical bonded structure. Take diatomic gases, like the oxygen and nitrogen we breathe. These are two atoms locked together by a central bond, acting like a rigid dumbbell suspended in a void. Because this molecule has a physical shape, it gains new ways to move through space. It is no longer limited to straight-line flight. This creates a mechanical conflict. If a thermometer only tracks straight-line speed, we have to account for what happens when the heat hits a molecule shaped to tumble and spin. To map this out, physicists use a concept called degrees of freedom. This is the exact number of independent coordinates, or dimensions, a molecule requires to describe its motion. Just like the single atom, our diatomic dumbbell possesses 3 translational degrees of freedom. It can move up and down, left and right, or forward and backward. But the dumbbell geometry creates 2 additional rotational degrees of freedom, allowing it to spin around 2 independent axes perpendicular to its center of mass. The molecule tumbles end over end around these specific axes. Rotation along the bond itself is negligible because its moment of inertia is too small to absorb significant energy. A diatomic molecule is a 5-dimensional geometric puzzle. It has 3 translational paths and 2 rotational ones, and that geometry dictates how it captures incoming energy. This behavior is governed by the law of equipartition of energy, a foundational rule of kinetic theory developed by Ludwig Boltzmann. Boltzmann's law states that in thermal equilibrium, energy spreads equally across every available path of motion. Every active degree of freedom receives an identical share of the total thermal energy. Mathematically, this is defined as 1/2 times the Boltzmann constant times temperature. In a single atom, the 3 degrees of freedom share the energy equally, with every joule dedicated to straight-line translation. But a diatomic molecule has 5 degrees of freedom. Any heat injected into the gas must be split 5 ways, linking the gas's thermal capacity to its molecular shape. Imagine hitting 2 gases with the same thermal energy pulse, monoatomic atoms on the left and diatomic dumbbells on the right. On the monoatomic side, heat pours entirely into translational degrees of freedom. The atoms fly faster in straight lines. The temperature gauge spikes. On the diatomic side, heat divides 5 ways. A significant portion is siphoned off to make the molecules spin. They rotate violently, while the temperature gauge barely moves. Energy siphoned into tumbling motion is energy that cannot be used to increase straight-line speed. Because temperature only measures translational velocity, this rotational energy effectively disappears from the thermometer. It is present in the system, but thermally invisible. This chart compares the steep temperature rise of a monoatomic gas against the shallow curve of a diatomic gas. We can think of this as our rotational tax. Reaching a specific temperature requires significantly more total heat because the molecule's shape demands a cut. Scientists measure this hidden energy cost as specific heat capacity. It is the physical evidence of a molecule's geometry. This is why the oxygen and nitrogen in our atmosphere act as a massive thermal sponge. They soak up solar energy to fuel molecular rotation, buffering the planet against rapid temperature changes. The physical structure of a gas dictates how it captures and hides energy. The geometry of the invisible world governs